just to recall what we have discussed in the last class. So we are actually discussing that it is one kind of modified Newton's method. There are actually several modifications of this method.
Sir.
Levenberg, yeah, tell me. Hello.
Hello, sir. Can we discuss, sir, exam pattern? Sir, 2 minutes.
Yeah, I'll discuss later.
Okay, sir.
Don't worry about the exam.
Sir, mid-semester exam, sir.
Yes, I understood.
Sir, someone said, sir, that exact pattern.
Exact pattern, it will be.
Sir, in last class you said some objective may be there, sir. That's why I was asking.
Okay, okay.
And sir,
Still, time is there, no? I have 30.
yes, yes.
Okay. So anyway, don't worry about it. Okay, so also we have seen that least squares problem. We have observed the linear case. So today we will try to look at the nonlinear least squares. But before that, let me just answer the last class question, that why do we consider that error terms E of AB, we have considered summation I equals to 1 to m, that yi minus ax plus b. Okay. The question was why we are considering this square term. Okay, we can have taken that this absolute values, this y minus y cap, yi minus y cap. If we take these errors also, then whether we will get the correct answer. Actually, statistically, depending on the situation, depending on the problem, sometimes this is preferred. Sometimes this is also preferred. So there is no actual concrete. There is no uniform theory that we should only consider about this one. One can take this one also, this absolute values. But if you consider this absolute values, the problem it remains. For example, if you think about f of x mod x, is it differentiable function? It is not. At x equals to 0, it is not a differentiable function. So when we have considered that del E del A equals to 0, that when we satisfy the necessary conditions, first order necessary conditions equals to 0, so we cannot apply those analytical formula for this purpose, because this error function, if we consider about this absolute values, so this is not going to be the mathematically correct. But statistically, where we do not use this differential coefficients, actually different derivatives, so in that case this works fine. In fact, there are lot of debate has been there for this purpose. I will share one article with you. So this debate has been coming since 1994 and then 1992, almost 100 years. So this has been published on 2005. So almost it is 90 years. At that time it was 90 years. Now it has been over 100 years. So this journal, it claims if we consider It is actually talking about the standard deviation and mean deviation. The same idea that error, actually this error function is similar to this standard deviation and mean deviation formula. So the idea is here like this. If we have this 10 numbers, and if we take the sum, if we take the deviation from the mean, okay, then so mean will be actually 100. So 100 total sum will be 100, and since it is so mu, that is mean, is actually 10. Now if you take the deviations from the mean of each numbers, so it will be some of the deviations are positive, some of them are negative. Now in standard deviation formula, it demands the square root of the average of the squares of the sum of the squares of the deviations. So this is 9, 3 square minus 4 square is 16. So 2 square is 4 and so on. Now if you take this summation and if you take this sum, it will be 40. And if you this is by 10, so this should be 10 because n is 10 number. So this is root over of 4. So this is 2. So a standard deviation, when we take the square terms, so it will be 2. Standard deviation will be 2. Okay. But if we think about this absolute values, just absolute difference, this is called mean deviation. So this summation will be 16 divided by 10. So this would be 1.6. So sigma in this case will be 1.6. So which is very close to this 2. Now there are some remarks that you can study. I will share this article with you for more. If you're interested in more details, so you can go through these details. Eddington has actually pointed that in calculating the mean error, that is the when we use the absolute error, the modulus value of a series of observations is preferable to the use of the simple mean irrespective of the sign. That is, the mean deviation is more preferable in some cases compared to the standard deviation, that is the square terms. So these two concepts are actually proposed in this 1914 and this 1920. One is called Fisher's model, another is Eddington's model. Okay. Now coming back to the problem, that linear, suppose we have 8 different data set. This is our x values are there, y values are there given, x axis and y axis. So you can take it in t variable and q variable. Now depending on this data, we can say that if we draw one straight line, then this can be the least square solution. Linear least square solution. We can also see in the right hand side that there is adjacent figure. If we think about this one kind of, suppose x into e power x, or here it is 2 variables, since this is 2 variable case, so we are considering, for example, here we have y equals to or q equals to e of t, the straight line we have written a1 into t plus a2. So this is one line. But if you think about this nonlinear case also, this is also possible. So this can also be our solution by suitable A1 for suitable A2 and A1. Okay. So how do we actually find this A1 and A2? That we have to understand. So that is actually part of the nonlinear least squares. Just to remember, to write the matrix form. So what we do is here, for I equals to 1, I equals to 2, I equals to 3, and so on, I equals to 8. If we write all the equations, all the straight line equation, because we have to satisfy all the points, but we have only two variable and 8 equations. So this is a very overestimated system, which is also known as inconsistent. Okay. But we have seen in the last class that we can find these approximate values by suitable transformations, finding the normal equations. So if you write it, so here it will be, okay, so just write it in a matrix form, A, X. Okay. Now in order to find this, X will be, if you try to find out A inverse of B. But this inverse is not possible because this is not a square matrix. Okay. So what we do is we define a function. Phi is a function of X, so that we write it as, remember this error function that we have defined, E of AB in this form. So here we will try to define this form. Phi of X is equals to this one. As you can see here, so this system can be written as AX minus B equals to 0. So our aim is to minimize the distances, minimize the error. This is the error term, which is actually, so for example, if you expand it and if you write it this form, so it will be like of this form. So if you write all these equations, okay, if you write all these equations, summation, so this will look like of this form. But if you write in the matrix form, it will look like this form. Okay. Now for finding the least squares, there is a theorem which says that the unique solution that minimizes this system is given by this formula. The proof is very simple here. So f of x equals to this one. So we write it down. If you, so this is a matrix norm, a square. So this is nothing but transpose of this one. If you just multiply and simplify it, now you take the gradient of this function and make it 0. So for first order necessary condition. So if you take this gradient, so this will become of this form. And from here, A transpose, for example, this is 2, 3, 4, 5, and 6, 7. For example, this is a matrix. And if you take the other actual matrix A and A transpose, so A matrix is 2, 4, 6, and then this is 3, 5, 7. So this is 3 by 2, 1, 2, 3, and 2, and this is 2 by 3. So multiplication can happen. So now you can see that this product A transpose A, you can see this is a 3 by 3 matrix. So a square matrix. If the determinant is non-zero, then there is a possibility that we can find the inverse of this problem. So, so inverse will exist if this is non-zero. Okay. So for this case, so what we knew earlier, we cannot do directly this inverse. Here from here, we could not find x equals to A inverse of B. So this was not possible here. So that is why we have to use this formula, this theorem. So by this theorem, it says, okay. Now it will give you the minimum value, because if you try to find out this Hessian, if you try to find out the delta 2 EFX, the second order partial derivatives, that is the Hessian matrix, then this will be always positive definite. The proof can also be given. So here it is a proof. Okay. So already we have seen. So the necessary condition is this one given, and for any non-zero vector x, we will have this relation satisfied, because norm is a positive quantity, or at least non-zero. But in this case, we will have non-zero, because all the differences are actually not equals. So at least one of them is not equal to. So we will have positive quantity. So Hessian matrix will be positive definite in this case. Now, if you try to find out in this is, so A matrix, you will find, I have calculated in Excel. So this is A matrix, A transpose. Okay, just transpose it, and then you have to find out A transpose into A. So this is a 2 by 8 matrix, and this is 8 by 2. So this is, the product will be 2 by 2 matrix. Okay. Now we have to take the inverse. So this is A transpose A inverse. If you calculate in Excel, and then the right hand side, this part is remaining. So A transpose, so this is A transpose, and B is there. So A transpose into B. So it will become, so this is 8 by 1. So 2 by 1. 1 by 8 by 1 matrix. So this one goes. So finally, this is 2 by 1. So this is 2 by 1 matrix. So these two and these two are matching the dimensions. So finally, you will get the X star. Equal to this one. So this is Q of t, that was the straight line. What we had, A1 t plus A2. So for example, this is minus 8. Sorry, minus 0.086 into t plus 0.86. So this is our least square solution. For this problem. Now, if you just recall, when we do not use this matrix form, just to that what we have discussed in the previous lecture, same thing, you just calculate the all the values and you try to find out this status. So this is almost similar. similar to the solution. So in this case, we do not use this. You can find directly from the data. Now it looks like, so if you, that the line that is, you are going to make it minus 0.86, for example, that was x plus 0.80. So y equals to this one, this line. So what is it? So that means we can write y plus 0.86, x equals to 80. Now when x equals to 0, y equals to 0.8. So 0.8. If y equals to 0, then x equals to 0.8 by 0.86. So this will be like 0.93 or something. Is it so? 0.8 divided by 0.86. So 0.93. So somewhere here. And so if you just draw the line, okay, it will look like almost this form. Okay. Now if we try to find out one nonlinear function which will actually approximate all the data set. So how to do that? Note that here we have a system of linear equations, m linear equations. So this was a 8 by the system of linear equations that we had. So similarly, we will have system of nonlinear equations. Okay. So for least square, we can use the linear equation, and we can take arbitrary function. It can be sine function, it can be cosine function, it can be also exponential function like this. The target is to minimize. What we have to do, we have to define a scalar valued function with the help of this function, because this will represent, what is this meaning? This b point are given, these b points are given. We want to find out the distance between the fx and the, sorry, this is yeah, fx, and this would be our fx. In such a case, that if we think about the nonlinear case, so these points are given, we have to find out the distances, and we want to minimize the total distances from all the points. From all the points we want to minimize the distances. So that is our distance. So from fx minus b, so we call it a norm, because in higher dimension case, distance is always represented by the norm, or better to write is actually 2 norm, L2 norm. Normally this is most popular norm that we use usually. So this is a Euclidean norm actually, norm 2. Anyway, when we are not writing, be sure that we are using the Euclidean norm, L2 norm. So for linear case, we have seen that we can apply this formula that we have to, this distance, we have to make it in as a scalar valued function. Otherwise, we cannot minimize. Scalar valued function means whatever may be the distance, okay, the domain, this is domain and the codomain, that is the range, it should be a real valued function, a scalar valued function. Okay, that means whatever you take, x1, x2 or xn, it should be a single identity, whether it can be x1 plus x2 plus xn, or it can be x1 square into x2 square into xn square. This resultant, it should not be in terms of tuple. Okay, it would be a single quantity. It is a scalar valued function. That is the meaning of scalar valued function. Because we want to find out, this is minimize. Like if you remember that we cannot compare 2 comma 3 or 3 comma 2. Who is minimum, who is not, we cannot compare. So in order to compare, so the resultant, the right hand side should be of the real number form, scalar valued form. We can, if they are actually belonging to real number set, then we can compare. Otherwise, if we have this tuple, so we cannot compare this. So that is why we have to make this form phi is a scalar valued function. Okay, now the target is to minimize this function. Originally, our target was to minimize the total distance from the function to the given point. Now we have done some modification, and with the help of it, we will try to minimize the distance actually. So if we can minimize this function, then we will actually minimize this total distance. So that is how we actually use mathematics to represent any physical problem in this form. We need to assume, we need to make some modifications as per the need. Okay. So for example, if we have a quadratic form, I mean, if you remember this, yeah, this can also be quadratic approach. Quadratic curve can also be like, suppose we have this form, we are not actually needing this part, so we can actually remain, if we can define 1 plus x square, or because this is a very simple case, so we have to take a generalized case, a0 a1x plus a2 x square. Maybe this can be represented, or maybe we can have, this is e power x a into a1 x. This can also be a possible least square. So our task will be finding the a2 and a1. Okay. So if we have this, whether it is linear or non-linear, so in this case we are talking about non-linear. So this is non-linear function. So model parameters will be, our aim is to find a1, a2 and a0, a1, a2. Now if we consider about the sine functions, then the model parameter will be a1, beta and phi. We have to find 3 different values. Now, how these are actually used, we'll see after some time. But the system of linear equation that will become, so A will be of this form, like this is 1 A0. So this is 1 1 1 1 1 1 all 1. So this is Ti square of this form. So we have to find out, because these values are given. These are xi values, Ti squares. These values are given. So this is A1, A2. No, sorry. These values will be T1, T2, and Ti, T1 square, T2 square, or and so on. So Qi values will also be given, Q1, Q2 also. These are given. Task is to find these values. Similarly, for if the function is given of this form, so then we have to find out A sine of beta Ti. So this would be A sine of beta T1 plus phi. Similarly, A sine beta T2 plus phi. A sine beta Tn plus phi. So all these values will be given. T1, T2, Tn values will be given. So Q1, Q2, Qn will be given. From this system, we have to find out these values A, beta, and phi. So that is our task. Yeah. So if you try to apply the same idea that we have discussed in the for linear case. So Q1 at this point we will write down this A2 into e power x if we consider exponential function. Okay. Because looking at the data, now the question will be how to decide whether we should take this this as a exponential or sine function. Okay. So in that case, I will have to show you that in fact it will be mentioned first of all it will be mentioned, or if it is not mentioned, then we have to understand from the given data. So how do we understand it? So let me just show you. Okay. So this is one kind of the data that we have discussed. Okay. So first of all, we have to plot it. So we have to plot it, for example, in a discrete plot, scatter plot. So this will not be good approach. Okay. So we can see that this is our plot. Okay. You can see this plot is of this form. The data set, if we plot in this, maybe you can use MATLAB also, no problem. So here, if you try to use this sine form, so it will not be a good approximation. But if you draw it here line, this may be a good approximation. But if you write of this form, this parabolic or this exponential, this may be a good approximation. Most of the time, this y equals to a2 e power a1 t. This may be mentioned. If it is not mentioned, then we have to look at the data. From there we have to understand. Okay, but if you have a different kind of data, this xi and x and yi are given, okay, of this form. Just if you just for example, this data is not here, only this 21 values are given. Okay, so from here you have to understand the scatter plot. Okay, so this is scatter plot will give you of this form. Okay. Now it actually looks like, if you think about one straight line, this is not a good approximation. Or if you think about this exponential, this is not also good approximation. So this can be only represented if we think about the periodic like sine or cosine function. Even cosine is not suitable for this curve, because cosine will start from here, it will go in this way. So sine function will be best fit for this data. Okay. So that's how we actually understand the function that we have to consider. Okay, now this function, what we can write is, suppose x equals to a1 and a2. So this system can be written as b equals to, this is b, f of x, or we can write f of x minus b equals to 0. So from here what we'll do, we'll try to minimize. We define one scalar valued function which is nothing but the distance between the points, fx points and the qi points. These are b points. So here the functions are actually, normally we do not take different functions. Every time we try to find out, for example, this is exponential e power x and this is f2 is sin x. We do not take of these different forms. We try to take all the functions as e power x type. Okay. So for this problem, it becomes this function f. F will be now a 1, f2, and fn of this form, which has n different. At each point, we are evaluating this point for even, and x is x1, x2, xn. We'll have this equation. So the target is to minimize this fx. We have defined this fx as of this form, and this x is nothing but a1 and a2. We have to find out a1, a2, and we have defined only, we are taking 2 variable case. We can take n variable case also, but here we have 8 data set, and we are trying to find out this exponential function. Okay, so this bi is nothing but the qi points. So we'll take the square values. Now if we try to differentiate it to find out the first, to satisfy the first order coefficients, So this, what it will be? So this is actually, remember, this is, we are supposed to write the A1, but since x1 and A1 we have to write of this form. Don't confuse with the notations. So here we can have, if we differentiate with respect to A1 for this function, so it will become 2 times 2 will come outside, 2 times this plus into this term will be here, and similarly A1 Ti is there, so Ti will be outside, another extra Ti will be there. Similarly, if we differentiate with respect to A2, so only this term will be evaluated, and this sigma is already there, so sigma will be here or also. Okay, so 2 times of this common portion, so this is the common quantity will be here, and then we have to evaluate these values, all this one. Now this is what, 2 equation in 2 unknowns, but note that these equations are not linear type. These are non-linear type equation, because u exponential e power x will be of this form. It is not linear. Now if you want to find out the Hessian matrix, we have to differentiate this second, this one, with respect to this. So Hessian, by definition, Hessian matrix is there. So all the, after differentiating, we have to substitute here. The expression can be much more bigger. So anyway, we'll see how to get these values. Okay. Now if you actually apply this Newton's method, Newton method says we have, this is Hessian matrix, inverse of Hessian, into the gradient, and this is the initial point or the previous point. So here it is fx. Okay, this is gradient. So once we find these values, these two values, we can apply Newton's method for least squares. In fact, from this least squares, we are getting actually these values. For example, we can take, because we have seen that, so for linear case, we have seen it was different. But if we assume this is the initial case of this form, so if you can iterate this form, so you may get the value. So what we can do is, if you substitute, this is A1 and A2, okay, you try to find out this x1. This is x0 now, and find out these values, substitute these values. There is analytical method. This two equations and two unknowns. After from here we can solve it. Okay. If you try to solve it, let me show you another solving methodology. You can use some Lingo software, which is called. So this is another. It is actually solving software tool, optimization tool actually software. Okay, so what you have to write from this gradient equals to 0. If you write it, so you will have two equations. This is one equation, this is another equation, and two variables. A2 and A1 are our variables. But since we have nonlinear functions, so e power x, e power a to the power a, all this point t1, and if you try to solve it, so this says that this is a feasible solution. It takes 24 iterations, and the final solution that is showing is this one. A2 equals to 1.7 and A1 equals to 1.2. Okay, so this is one way to solve this nonlinear system of equations. Okay, right. We will now try to find out the working formula for this nonlinear least squares. So this is already discussed. We have discussed already. Yeah, right. So for Newton's method, the Hessian matrix will be of this form. This is a gradient we have seen, and then we have seen the Hessian matrix of this form. Okay. We'll discuss the formula again, but we have to understand the mathematics behind this formula. So how do we get this formula actually? So let us discuss of this. What is it? For example, f of x is given summation fi square I equals to 1 to m, or maybe I equals to 1 to m. Then what we can write? F1 square. Sorry, this is not important. This is not needed. So not so far now. This one. And this is nothing but the phi of x function type. We have to define that yi minus a sine of omega ti plus phi of whole square. So this Ri can be defined of this form. If we have the data set of this form, so it is natural to it is trivial to find out this this error function can be defined in this form as a nonlinear function. Okay. Now what we have to do, we have to find out that nonlinear a sine omega ti plus phi, all the values. We have a system of linear equations f of f1x of 0, f2x of 0, and f of n x of 0. So this is a system of linear equations that we have. Okay. Now here we have to use the derivative method, because first order conditions we have to satisfy, and then we have to find out the second order Hessian second order derivatives, also partial derivatives. So for a given function, what can be the derivative, the jth component? Okay, let us not discuss of this form. So if we have how this formula has come, we will discuss with them. Let me just write here. So if our function f of x is given of this form 1 to f of fi of x square. Okay. So this is same as writing fi square x. Don't be confused. X is our x1, x2, or xn transpose. That means we have n variable function, n tuple. Okay. Then if we differentiate this function, with respect to xj, some particular xj, then what will be the, or if we just write it for x1 with respect to x1, x2, xn, then what will be the derivatives? Lf x1. So this will become, okay, let us expand this formula of this form, fix f1 square plus f2 x square plus fm square. Okay, then what happens is 2 times f1x because this is x term, it has n components. So we are considering only x1 terms. So this will be the partial derivative of f1 with respect to x1. Similarly, for this one, 2 times f2 of x. f2 will remain same and another partial derivative with respect to f plus, in this way we will have fm del of fm del x1. Okay. Similarly, del of x2 will be 2 times f1 of x into del of f1 del x2 plus, and so on, fm x into del fm by del x2 and so on. So in general, we can write it of this form: summation 2 comes outside, or let us write expand all the formulas. Del x n different components are there. So 2 f of f1x f of f1 into del f1 del x1. Sorry, 2 will be there always. 2 is already there. 2 multiplication will be always there. So this is del f fm del xn. Okay. So if you just try to simplify, if you write in the matrix form, what will be there? So let us take 2 outside. So 2 will be outside. So if you write it, that the gradient of f x equals to, this can be written as of this form. Okay, 2 outside del ff1 del f1 del x1. Okay, then del f2 del x1 into del f of m del x1. And if you write it on this form, f1x f2x fmx. So similarly, we can have this one as del f del xn 1 del f2 del xn del fm del xn. Now, are you familiar with this notation, with this matrix?
Jacobian.
Yes, but it should be the transpose. The Jacobian is actually of this form. del of f1 del x1 del of f1 del x2 del of fm by del xn, sorry, f1. Okay. Fm so this is Jacobian, but we have here is Jacobian transpose. Okay. So this gradient of f, we have 2 times Jacobian of x transpose into what we are having. This is, let us call it f of x, f1x. So this is f of x. So this is our Jacob gradient now. Okay. Now, if you look at this formula, what is actually happening in this case? Del f del xj. This is nothing but 2 times summation I equals to 1 to m fi of x into tail of fi tail of x j. So this is our actually if you look at this expression, this can be expressed in this form. Okay. Now if we differentiate again this one, because we want to find out the Hessian. With respect to, for example, k, for all k equals to 1, 2, n difference. Okay. Because we want to find out the second order differentials. So this could be find out so for this case, so let us write g k into j. Okay. If you differentiate it, what will happen? So 2 will be there, already 2 is there. Then m will be there, I equals to 1 is there, right? So we have to multiply, we have to, I mean, this del k will be this form, f of fix into del of fi del xj. So this is nothing but del 2 f xj kj. So this is 2 times m I equals to 1. This would be del fi and then del xk into del of fi del xj plus, okay, when we are differentiating this one and this one remains constant, but we have to, when this is constant fix, so we'll have del 2 fi del x k del x j. Okay. So this is our. Now if you look at this function, if you look at this, so this is again, this is kind of j transpose, and this is again j, the Jacobian, because I varies from 1 to m and j varies from k and j, this varies from 1 to k, 1 to n. So that is why we will have a matrix of this form m by n. So this would be n by n actually, n by n. Another matrix will be m by n. So these two matrices are Jacobians. Okay. And here when k equals to j, then we will have, for example, del 2 f1 del x1 2 of this, that is diagonal elements. Okay. If you remember, for two variable case, Hessian matrix was 2 del 2 f1 del x1 2 del 2 f1 del 2 f del x1 del x2 then del 2 f del x1 del x2 del 2 f del x1 del x2, sorry, del x2 of 2. So this is the Hessian matrix. Okay, but for this is a more generalized case that we are considering. So k and I at jth entry of the Hessian matrix. So the k jth entry, k jth element of the Hessian matrix for this case is this one. Okay, but it has sigma fi multiplied, xi is multiplied here. So we have to refresh, we have to rewrite this expression. Okay, and this one, let us call it fi x, and this one will be called Hessian matrix. Okay, because if you again find that I equals to 1, like this case, because this would be Hessian and this would be fx when summation into all these terms are there. So this j I kj g of kj becomes 2 times jx transpose, that is a Jacobian transpose, and then Jacobian plus 2 times of this f of xi I equals to 1 pm Hessian. So if you just write down, for example, g of x, all the, if you consider all the derivatives, that is the Hessian, this will become This is actually Hessian matrix of Y, because we have to understand that we are having now m different functions. So for f of fi, the Hessian will be hi of x. Okay. For f2, the Hessian will be h2 of x, and so on. Okay. So if you let us recall the gradient that we have, yeah, here it is. Delta of f of x is this one. So delta f of x, we have 2 times Jacobian transpose of f of x. Okay, right. Then, so since this is Kij term, so if you write it in a matrix form, so it will be like of so g of x, we call it g of x. So this will be, so let us call it a t of x, just giving another name, because Hessian matrix is already found here. So this summation, we call it a t of x. So this j will be 2 times j transpose of j of x. Let us call it 1, 2. And if you remember, sk, that is the direction matrix that we calculate in Newton's method, which is negative of Hessian inverse into that the gradient at xk at that point. Okay, so this is 3 equation. Okay, so this is actually, so g of x is actually plus 2 times tx. Okay, from here, or we can also write g of x equals to two times j x j transpose jx minus t of x. So we want to find out that xk plus 1 equals to xk plus sk. That is the iterative formula for Newton's method. We want to find this. But from these equations, so this gradient, and this is related to the function that we have calculated just now, which is the Hessian. Okay. This is the Hessian. Sorry, this is, I think I have written something wrong. Okay, so from here, let us write Sk will be Sk times the Hessian. If you Hessian into Hessian inverse Hessian into the Sk, it will be negative gradient of f of x. Okay. Because we have this relation, so from 3 we can have this relation. So now we have actually this Hessian as, in this case our Hessian will be the gx. So this is 2 times g transpose the Jacobian x plus t into Sk, and we have already, this is the gradient we have seen, this is negative 2 times j, that Jacobian transpose into f of x. Okay. So this 2 and these 2 gets cancelled. So here you will get that f of x or the Sk, this direction, what we will get, x transpose jx plus tx inverse of jx transpose into fx, and this is negative. Now if you look at the formula that we have found earlier for the linear case also, it will look like actually similar. So xk will be xk plus 1, xk plus sk. Now for if we allow this matrix to be 0, then the formula it becomes, if we are neglecting this term, then this formula will become of this form. So let us not write x again, j transpose j of inverse j transpose of f. So this is nothing but very similar to the problem that we have discussed for of this form, x star equals to eta of b. E is the f of x value. So this is very similar to the x star that we have calculated, A transpose A of inverse A transpose B, or least square. So now we can see that the working formula, actually this formula is known as Gauss-Newton method. I will tell. So yeah. So from here we'll discuss again. So these are the equations that we have. We have found the Jacobian, then the gradient, and then we have found the Hessian matrix. The I, K, J term component of the Hessian matrix will be calculated of this form. And this Hessian matrix that we have are actually denoted by of this one. So this is they are calling it Sx, where I have called it Tx. So the Hessian matrix will be of this form for this particular problem, because this is Hix, Hessian for a particular component of the function. So the total entry will give us the Hessian matrix, and this is only one entry, Ki entry of the Hessian matrix. So this function is actually, this method is known as Gauss-Newton method, where we are taking this Sx to 0. We neglect the value of Sx equals to 0. So then it will be reduced to of this form. So when we do this formula, then this method is called Gauss-Newton method. And in fact, you can see that because we are neglecting this formula, what we can say, we are approximating the xk plus 1 by only Jacobian only contains the first order differential coefficients. We do not have the second order coefficients. In fact, this second order coefficients will be very, very close to 0. So that is why we can neglect them, and this can be used to find out the optimal solution, to the minimum solution, the minimum value. Okay. Now, if you try to look at some example that we have discussed, yeah, the example that we have started. Okay, so these are 21 values I equals to. So for this particular values is given. So we'll use this Gaussian-Newton algorithm to find out the values. I'll share one actually PDF where MATLAB codes are given. So you just have to do the debugging. I mean, from according to the problem, you have to set up the codes. Now there is one problem in Gauss-Newton method. If this matrix is not positive definite, then what we'll do? Then we'll go to the last class that we have discussed, Levenberg-Marquardt method. We will impose one particular this mu k value, which is large value, so that the resultant becomes a positive definite matrix. Okay. So if this can happen, this happens, then we have to go for this. So both of these are actually non-linear least squares problem. So I will share, try to verify this method. Let me just open one. Yeah, so here it is. This. So Levenberg-Marquardt method, it is already discussed in the last class. You can find this actually MATLAB code. You have to debug this code. You have to set up the code according to your problem. The instructions are given here. So you can verify these results, whether they are correct or not. Similarly, this Gauss-Newton method that we have discussed for the last two class, that is Levenberg-Marquardt method, and this this Gaussian method we will discuss next class, Gauss-Newton method. For nonlinear, all type of problems it is given. Okay, let me just. Okay. Yeah, so here it is. Yeah, Gauss-Newton method. So here you can see that exam equations are given. They have tried to do the same thing that we have discussed just now. The Hessian matrix is almost equal to, because they are actually approximating, making the Sx equals to 0, and the function becomes of this form. So one example is also they have discussed. So try to implement this Gauss-Newton method. See the code, try to debug it, and you'll be able to find out the solutions.
Doctor, I'm not sure which book you are referring to here.
No, I have not shared this book. This book I have actually downloaded just 2 days back.
Okay, okay.
Okay, so I will share this book.
Oh, God bless you. Okay, okay. Yeah, thanks.
Okay. So, I mean, no single book can offer everything. Okay, so that is why I am reading several different books so that it can be useful for all of you. Okay. Apart from this, if you have any doubt, you can ask me.